Hey guys, this is Mrs. Harvin, and we are continuing in Chapter 3 of Pre-Calculus, and today we are going to take a look at trig functions, Lesson 3.5. Now, this is a really lengthy lesson. I honestly don't think that I can get this done in one 15-minute presentation, so I'm going to try and get through the first 2/3 and then make this final third a separate presentation. So you probably are going to have 2 videos for this lesson. Now, there is a little note here on this first slide that we are going to be working with trig functions. So you do need to make sure that your calculators are in radians when you are doing anything on your graphing calculator. Our biblical integration for this unit continues to be this: God creates seasons for all areas of his creation. Good times and bad, life and death, winter, spring, summer, and fall. These are just a few of the cycles that we see in God's creation. And trig functions, as we looked at the last lesson, are a type of repetitive or periodic function, and they fit into this pattern and this cycle of God's creation. Our lesson objective for today is that you, the student, will define the trig functions. You will determine periods, amplitudes, phase shifts, domain, and ranges for the trig functions, and you will be able to graph them. So let's take a quick flashback and review those trig ratios. Those 3 common trig ratios are sine, which is opposite over hypotenuse, cosine, which is adjacent over hypotenuse, and tangent, which is opposite over adjacent. Now, remember that we did this back at the beginning of the year when we were trying to find the missing measurements or missing angles of a right triangle. Remember, trig ratios are only for right triangles. And if I were trying to find this angle, for example, I could use what I know about the sides and the ratios between those sides to help me determine angles, or vice versa. If I knew the angles, then I could use what I knew about these ratios and right triangles to determine the sides. We then looked at how these trig ratios are incorporated inside the unit circle, because inside the unit circle we can create right triangles, and we can use that same information to help us find angle measures. Now, angles can be measured in either radians or degrees. Typically in geometry, you're measuring angles in degrees, but what we have learned when using trig ratios and when looking at the unit circle is that we're going to typically use radians, which means we're going to leave everything in terms of pi, pi over 2 or 3 pi over 2. That's more precise than decimals. Degrees, we always have to round, and so we lose some of that precision. So we're going to leave things in radians, which is why if you're using your graphing calculator, you need to make sure that it's set in radians and not in degrees. Now let's take a look at some trig functions. Now that we reminded ourselves of those 3 main trig ratios, the trig functions are this: f of x equals sine x. Remember, f of x is just another way to express y. So f of x equals sine x, where x is an angle measured in radians. Remember that we did talk about that we will often see theta used instead of x for our variable here. F of x equals cosine x, where x is an angle measured in radians, and f of x equals tan x, where x is an angle measured in radians. So these are our 3 definitions of the sine function, the cosine function, and the tangent function. That should be easy to remember. This is our function notation, and this is sine, so sine function. Okay? Not too difficult. Hopefully you got those 3 definitions. If we were going to find the set of ordered pairs described by f of x equals sine x or y equals sine x, this is our sine function, where the domain is these 3 numbers. All we would have to do, just like in any other function, is plug and chug. And so pause just for a second, plug those into your calculator, resume the video when you're ready to check your answers. All right, hopefully you put those into your calculator and you've got 0.1736. So our 0.175, 1745 is what we plugged in, and when we calculate that, we get 0.1736 as our sine value. Let's find the sine of 0.3840 and the sine of 1.2392. Right, so that's just a matter of plugging and chugging, and then you can list each of those as coordinates here. Here's our angle, and here's the sine of that angle. When looking at our sine and cosine values, if you're familiar, hopefully by now you're feeling really familiar with those unit circle values, you should notice that the range of both the sine and cosine functions, y is greater than or equal to -1 or less than or equal to -1. When going around our unit circle and listing those coordinates like you just did on a previous quiz, you should have realized that your sine value and your cosine value, both of them, neither went over 1 or below -1. They stayed in that range. So they do have that same range. The domain of both is the set of all real numbers. So a range is always between -1 and 1, but the domain is all real numbers when we're talking about sine and cosine. Now what about angles that are greater than 2 pi or less than 0? Going back to that unit circle, greater than 2 pi. What if we go around the circle more than once? Well, hopefully you remember, and you've learned from our previous lesson on periodic functions, that the trig values for these angles are found using a reference angle. So they also have a range of -1 and 1. Remember, we did all that work with periodic functions, finding things like find the sine of, 59 pi over 3. And we referred to that unit circle, we found the reference angle, and we determined that the sine was the same as that reference angle. So even for angles greater than 2 pi, because we're using a reference angle, that range will still be between -1 and 1. Now on a unit circle, which you should be familiar with already, P of x and y is the same as P of cosine theta sine theta. We've talked a lot about how x is first in the alphabet, y is second, cosine is first in our coordinates, and sine is second. If we're putting things in alphabetical order, we've got x and y, cosine and sine. Both of those are in alphabetical order. All right, let's take a look at what the sine function looks like when we graph it on a Cartesian plane. Now notice, because I'm using radians here, my x-axis is not going to be labeled 1, 2, 3, 4, 5 like it typically is when we're doing integers. Instead, I'm going to label the points on my x-axis with our radians here. So I've got pi over 2, pi, 3 pi over 2, 2 pi. So I've got my x-axis labeled with my radians. And we know that when at the beginning of that unit circle, when we're at 0 radians here, we know that our sine is also 0 because we are so familiar with that unit circle. And we know that when we get up to pi over 2 or 90 degrees on the unit circle, our sine value is 1. If we continue to graph that function, we're going to see that at pi, our sine returns back to 0. And if we continue to graph that function, eventually our sine function will look like this. You can tell just by looking at it that this is periodic. You can see that those periods are repeating. It's got this wave, which we talked about. Waves were a periodic function. So this is a picture of the sine function. Let's take a look at where its axis of symmetry is. Is it symmetric across the y-axis? Is it symmetric across the x-axis? Or is it symmetric across the origin? Okay, hopefully you realize that the sine function is symmetric across the origin. Okay, this is our line of symmetry here across that origin. It's just kind of like this piece is picked up and flipped over the origin. And functions that are symmetric across the origin are odd functions, going back to what we learned about polynomials. Therefore, the sine of negative theta is the same as negative sine theta. Let's take a look at what that looks like on the unit circle. So we said the sine of negative theta is the same as negative sine theta. All right, so let's take the sine of negative pi over 4. All right, negative pi over 4 is right here. And the sine of that is negative root 2 over 2. And that should be the same as negative sine pi over 4. Well, sine pi over 4 is up here. So that would be negative root 2 over 2. So we've got the same thing. Sine of negative pi over 4 is negative root 2 over 2. And the negative sine of pi over 4 is also negative root 2 over 2. So we've taken this definition here of an odd function, and we have plugged in some numbers, and we see that that is the case. the sine of a negative angle is the same as the negative sine of that positive angle. And we just used pi over 4 as our example there. So again, the sine function is symmetric across the origin. It is an odd function, and this is true of odd functions. When looking at the cosine function, if we were to graph that, we know that, again, our x-axis is labeled in radians here, and at 0 radians at the beginning of that circle, my cosine is 1. As we move around the unit circle and get up to pi over 2, or 90 degrees, our cosine is 0. And if we were to continue to graph each of those points, we would get a cosine function that looks like this. Also periodic, also a wave, but a little bit different from the sine function. If we're looking at the axis of symmetry here, we can see that the cosine function is symmetric across the y-axis. So just like a quadratic function, if you remember, quadratic functions are symmetric across the y-axis here. And the cosine function is symmetric across the y-axis, and it is therefore an even function. And in even functions, the cosine of a negative angle is equal to the cosine of the positive angle. Let's go back here and see. So the cosine of negative, let's just stick with pi over 4. Cosine of negative pi over 4, right here. Cosine of negative pi over 4 is root 2 over 2. And that should be equal to the cosine of a positive pi over 4. And let's see if that's the case. Cosine of positive pi over 4 is also root 2 over 2. So our definition is true. Cosine function is symmetric across the y-axis and therefore an even function. Pause just for a second and see if you can think of some other even functions or odd functions. Or how do we determine in our polynomials if they're even or odd? Hopefully you remember it was the degree of the function. The degree of the function is determined by that highest exponent. So if that exponent was odd, then that was an odd function. That kind of looked like this, symmetric across the origin. But if that exponent was even, like an x to the 4th, then we were symmetric across the y-axis, and it looked something like this. Okay, so sine and cosine, even though they don't have those exponents, are still determined or defined as even and odd. Sine is odd, cosine is even. All right, a second objective that we had for today is that you will be able to determine the amplitude of a function. Now, if you're familiar with the idea of waves in science, then you've heard this term amplitude before. And here's the official definition. The amplitude is the absolute value of half the difference between the maximum and minimum values of the function. Right, so when we're talking about waves, basically this is our x-axis here. Draw my x-axis. It's not very well drawn. Okay. Our amplitude is how high that wave is. Okay, so we start with the center of that wave when we want to know how high that wave is. In order to find that, we take the minimum, we subtract the maximum, put it in absolute value, and divide it in half. So there's our actual formula. Amplitude is the minimum minus the maximum divided in 2, and we want the absolute value of that because we want to know the height, and you can't have negative height. For both sine functions and cosine functions, the amplitude is 1. So if we were to go back to that picture of the sine function, remember as high and as low as they go here is 1 and negative 1. So our amplitude, or the height of our function, is 1. If we were to plug that into the formula, we would have negative 1 minus 1 divided by 2, and we would want the absolute value of that, which also equals 1. So in general, for our sine and cosine functions, if we have a number here in front of sine theta or a number in front of cosine theta, we're going to represent that with a, and that's going to stand for amplitude. So putting an integer before sine, or rational number before sine or cosine, is going to change our amplitude. So let's take a look at what that looks like, and this is our last example in this first video. If we were to graph f of x, or y, equals 2 sine theta, okay, this is just like our regular sine theta function that we've already graphed, but our amplitude now is going to be 2. So instead of going up to 1 at pi over 2, we're going to go all the way up to 2 at pi over 2. Our zeros are